this next section, we're not going further than 12.3 today. 12.3 is dot product. We'll go close to everyone. I'm thinking right. You know, remember I want to leave time to end of class? I'll leave that time to end of class so I can meet with people. They have things they want to talk about. Let me sign some stuff. This is the dot product of two vectors. Now I have to define it. Remember that formula sheet I passed out? It's on there. And that's why I gave this to you. I've already put in Canvas every formula we encounter in this course. I didn't want to hand that out the first day though. Isn't that too much? But if you wanted to see I want to see how these formulas keep going along. There's a lot of these. They just over and over again. Well, this definition of a dot product. Two vectors. I call this vector A. And now let's say these are the components of vector A. I'll just call this A1, A2, and A3. Is that okay if I call those the components, the X, Y, and Z components of vector A? I'll make it three-dimensional. And here's vector B. It's got components B1, B sub 2, B sub 3. This is the definition of a dot product of two vectors. Vector A, dot, and when that dot, they make it pretty big, okay, in calculus manuals. That dot's pretty fairly big. You can check the textbook how big it is. It's not huge, but it's more than just a speck, okay? It'll have some size, that dot, so you see it. It's not that, the multiplication symbol we use a lot? It's a light dot. It's a little better. And it's an easy, easy definition. It's this. I'll write it out. This times this, plus this times this, plus this times this. That's the definition of a dot product. Let me do it again. What's the dot product of A dot B? Vector A dot vector B. I multiply those two X components. I put a plus. I multiply these two components, plus, multiply these. So do you notice something when the dot product is not a vector? So let's write that down, so don't forget that. The dot product of two vectors is not a vector, right? It's important we know that. But relatively, the dot product of two vectors just becomes a scalar value. Or just call it a scalar. And scalar is spelled S-C-A-L-A-R. You're like a number, right? It's not a vector. You go, why did they do this? It's neat. Just by this definition, this dot product emerges into all these cool areas of calculus. Really helps us do things. Like find the angle between, three different vectors in three-dimensional space. So if I wrote this out, everyone, as a definition, I don't think I have to write it all out. But let me do it again. It's simply what? This times this, plus this times this, plus this times this. Cool. Can you get negative answers? Sure. Can you get answers of 0? Sure. Can you get answers like 100? Sure. Well, let's do an example. You're 1, 5, negative 3, you're 2, 4, 8. I am telling you, everyone, no matter how big these numbers are, I think you'll be able to do this stuff mentally. They're usually not too, when you do dot products, you'll be able to look at it and go, I can get this. But if you have to, write it down. What is A dot B?
2.
2 plus up
20.
20 minus up
24.
and what's 22 minus 24? That's the dot product.
What does it actually mean though?
I know. I love this. He goes, what's that doing? Right now when it's just a definition. Stated definition. But what's neat is by that definition, all this usefulness gets applied. So the first one I gotta write down, I'm gonna put. Now I've been deriving things all day. A little hot in here, I'm like, I won't derive this next theorem, everyone. What I mean is I won't prove it, but the proof is in the books and it's pretty clear. I do want to point out this theorem I'm about to write on the board. It's proven by the law of cosines. Anyone ever heard of the law of cosines before? Cool. So if you're really into math proof, like I want to see the proof for this. So there's the definition. He asked a really good question like, well, what does that mean? Right now it just has no meaning to us. It's just a definition. It comes up with a number. What does this mean? But cool theorems like this emerge, right? A dot B, the dot product of any two vectors will always equal this. And if you're curious, like if you wanted to prove this, I won't now, number one, I think I'd bore you. Obvious, some things are cool, I think this would bore. It's not like it's 3 steps, it's more like 12 to 15 steps. And you'd be like, 15 minutes from now, you'd be like, would he just stop? Can we do some problems? It's in the book too. But this is true. Now this is a powerful, powerful theorem. So give it 5 stars. What it says is the dot product of A and B, two vectors, A dot B will always equal the magnitude of A times the magnitude of B times the cosine of theta. And you go, what's theta? Theta is the angle between those two vectors. Theta is the angle between those two vectors. Cool? So,
How do you find the theta when you have like A and B like?
oh, good. So let me draw it right here. Whoop. Whoop. Let's just say that was A. That was vector B. When it's written like that, where's the theta?
Between A and B.
You got it. Now, you go, what if one's over here and one's over there? You're always allowed to take vectors and slide them, aren't you? That's what I want you to remember. You can always take vectors and slide them anywhere. So you got them so you can see what that angle is if you wanted to. So, this is huge, everyone. Are you ready? What do I have here? Oh, I gotta have 2 markers. And can we call my tips the arrows? Right? The tips of mark, I gotta be careful because I always said, you're the tails of the vector, right? You know, or excuse me, tip, and then I'll call this the tail. Just so I'm clear. Alright? So if I had this, I can say, oh, you're the tip of the vector, but you're the what?
Tail.
You're the tail. Well, how about these are the tips? What do you think this dot product would be? Let's use that theorem to figure it out. I got these at 90 degrees. I got these two vectors at 90 degrees. What do you think the dot product of any two perpendicular
Zero.
vectors is?
0.
Now, how do you know it's 0? It's all about that angle. What's that angle?
0.
90 degrees. So that's how this theorem is so powerful. We can now take this and extend this and put something down in our notes and say that the dot product of two perpendicular vectors will always result in what? 0. You go, is it a hard theorem to prove? No, it's easy. Because the cosine of 90 degrees is
0.
0. And that's what you get. And it's an easy way to identify where we got perpendicular vectors in space. Now there's some other names for that word perpendicular. The first one popular is orthogonal. So you can read it in the textbook and be like, find two vectors that are you can hear this orthogonal. They're talking about perpendicular. Right? There's another vector, you go, the vector is normal to the plane. And you go, normal? They're talking about the vector is perpendicular to plane. So those 3 words go hand in hand. Perpendicular, orthogonal, and
Normal.
normal. I just want to let you know that. Alright? So, the dot product of any two vectors that are perpendicular will always equal what?
0.
0. Alright. Well then, now that we know that, let's try something. And let's find the angle. I need some points in space. Here's P. Here's Q. And here's R. 0, 1, 2. 1, 2, 1. 3, 1, 4. Those are 3 points in 3-dimensional space. So can we find the angle between PQ and vector PR? Let's find that angle. What theorem will help us do this? That one. I mean, this is amazing. We're talking, this is just 3 points in space. Think of it, if they ever have to take geometry class, Like I took geometry, it never went three-dimensional, but I remember every once in a while we get that bonus question. If I just had limited knowledge of vectors and like just dot products, I could get all these answers. Because now you can turn this into vectors and just get the what? That angle. You want to rearrange this? What would cosine theta equal every time? In this theorem. Cosine of theta will equal A dot B, right? Divided by the magnitude of A. Magnitude of B, is you agree?
Mhm.
I'll write this one more time. What's theta equal to? It's the inverse cosine of. I mean, you might want to type it like this in your TID 384. There you go. It depends though. I want to get that new math print mode where it allows you to write the fractions like this. I don't. Looks all neat. Alright, Owen, but there's something we haven't even done in this class yet. These are not vectors. Those are vectors. These are what?
Coordinates.
So make a note of that, like, those got the solve trick, those are points. So the first step, as we're gonna try to solve this problem, everyone, we need vectors. And I haven't done this yet in this class. How do you get vectors from points? How do we do that? How do I get vectors? There's gotta be a math technique. It's gonna be simple, by the way. But we have yet to do this in this class. I wanted to wait till now to do this. How do you get vector representations from points? And it's cool, everyone. All we do is tip minus tail. That's all we have to do. We just do simply tip minus tail. So there's point P, Q, and R, right? Let's find vector PQ. How do I figure it out? The three components. Everyone, let me say it again. Tip minus tail. Well then Q is the what? The tip? The tail is P? What's 1 minus 0?
1.
What's 2 minus 1? And one more.
Negative.
What's
1.
1 minus 2? Did anyone see that? Important step, I don't want to rush this at all. You go, how do I go from points to vector representation? I've got 2 points. We say you just do the tip minus the tail. So if it's P to Q, I go up to Q and I just subtract. I subtract the components. So what's PR then?
3 minus 1. 1 minus
3, there's P, there's R. 3 minus 0 is
3.
3.
Sorry.
1 minus 1, let me get a common here, sorry everyone.
0.
0?
And 4 minus 2.
2. So and here's like some PQ, there, it's going like that. There's some PR, but they're in 3-dimensional space, aren't they? We have to draw. Now can we get the angle? Oh yeah, we'll do the dot product of them. Remember, the dot product is just going to be a scalar value. We'll divide out the magnitude PQ and divide out the magnitude of what? PR. Sound good? All right, let's start out with the dot product. Everyone okay with this? Mm-hmm. Nice. Now, what's PQ dot PR? This is the thing you usually can do in your head. You'll find yourself never grabbing a calculator on this. But if you have to, go ahead. Because 1 times 3, everyone, is not 4. What's 1 times 3?
3.
So 1 times 3, 3 plus
0.
1 times 0 is 0 plus negative 2.
2.
So 3 plus negative 2 plus 0 is?
1.
Everybody agree? Isn't that neat? Sometimes you get a nice 1. So I have a question for you. Is the angle 90 degrees? No, I don't know what the angle is, but it's not 90. To be 90, that would have came out to be what? 0. Right away, you would have known. You'd be like, dot product 0, it's a 90-degree angle, right? That would have been cool if I got lucky. You saw me making up numbers. I was just making up numbers in space. That would have been neat. All right, we got that. That'll go there. And what's this? All right, so I'll start writing this. Theta equals inverse cosine 1 divided by, what's that magnitude? Square root of that squared plus that squared plus that squared.
Square root of 3.
Square root of 3. Does everyone agree? See, that squared is not a negative 1. That becomes a what? 1, you squared it, you get a 1. 1 plus 1 plus 1, you get a square root of 3. All right, right next to it? What's that magnitude?
13. Square root of 13.
Man, you are getting fast at doing magnitudes in your head. 9 plus 0 plus 4 is?
13.
Now, it depends on your calculator. And how are you going to type that in? You know, just be careful. What mode?
Degree.
Degree mode. You know, you might, here's me. I'll tell you me, my calculator isn't so fancy. I take it a step further and I'm worried that I'm gonna mess up that denominator. So I'll multiply the 3 times the 13 and make one radical. What's this 3 times the 13? Yeah, that's what I'll type in. Seriously, I'm like, it doesn't hurt me just to multiply these, because I'm worried this thing is not so fancy. It's like the old school classic mode, and sometimes it might give me the wrong answer if I don't type it in properly, and I'm like, well, let me just do 1 divided root 39. All right, let me check my mode. Yep, I'm in degree mode. Inverse cos, 1 divided by square root of 39. What do y'all get?
80.7.
Almost 90 degrees, 80.78 degrees. Wow, they're like three-dimensional space. Isn't that cool? But if you do have like a brother or sister or someone take a geometry class, next time they get like a bonus question about find an angle, I am telling you, just turn them into vectors. You can do anything. You can find any angle. It's all you gotta do is take points, make them vectors. My gosh, you had to do this.
And on a two-dimensional plane, like they were working with that, we would just use the X, Y.
I'm so glad you asked that, because I might have forgot to say that, and shame on me. This works in two-dimensional space, you know? And what about the dot product? You know, let's try it. Ready? The points are 1, 3, 2, 7. Point R is 3, 11. All right. Well, the first thing is we need vectors. What's PQ?
1 and 4.